Hello everyone, welcome to this second video in this series video. In this video, we will discuss how can we use the practical method to get the parameter time constant from a first order transfer function. So in this video, we could have two subtopics. The firstly, which kind of process can use the first order transfer function to represent. Second, once we identify one system can use the first order transfer function, then the second topic, how can we get the time constant, or we call exponential frequency parameter from this first order transfer function. Okay, let's talk about the first topic. So let's firstly quick review this example. So in this example, it's asking how can we get the DC motor and its load transfer function. But frankly speaking, from the practical engineering view, this is horrible because to get this transfer function eventually here, we need to get the mechanical constant, the inertia, and the armature from the motor. And a very simple question, DC motor, if we have other system, for example, a heater temperature system or other system. So if using the calculation way is really hard, can we use some engineering way to get the first order transfer function? The answer is yes. So firstly, we need to identify if the first order system can represent your system. So the easy way, or from my personal experience, we can give the system a step response, and let's watch the system response, the curve. For example, if we are going to get the transfer function from a DC motor, basically we know the DC motor could react as a first order system. We can apply a voltage. Voltage runs as input, and then we can monitor its speed. The speed is the motor output, right? So typically, when we apply the voltage to a motor, if we are going to use PLC to control the DC motor driver or even the AC motor, we are using the PLC to apply the 0 to 10 volts, connect to the VFD, VFD connect to the motor. So basically the motor drive, the input signal is 0 to 10 volts. And the speed of the motor that could react from the 0 to, for example, 2000 RPM. Okay? Therefore, firstly, we need to identify the input signal and the output signal from your object system. And the behavior of this motor, if we are going to use the PLC, so we can record the reaction curve. Then we can use HMI or PLC curve function to record the voltage input signal and speed feedback signal. This curve, this is the time. Then the y-axis, this is the voltage input and the speed output. Okay? When we apply a bump test to the control input signal, we give a 0 from the 0 volt to the 2 volt signal. Then we will see the motor will react like this. The motor will react like this. So if you see the curve like this style, basically we could see this curve react as the first order transfer function behavior. Okay? And when we apply 0 to 2 volts, eventually, for example, we can get a 5 RPM. This curve shape shows exponential shape. So if you see your process system react like this style, basically we could use the first order transfer function to represent this process system. If you are using a heater system, from the PLC output, maybe you are using the analog output. The analog output could be the 0 to 20 milliamp or 4 to 20 milliamp, right? And in your PLC program, your 0 to 20 milliamp could represent as 0 to 27, 6, 48, the unscale function here. For example, when you apply the 12 milliamp to the regulator, so basically the 12 milliamp that come from your analog output card. But the analog output card is controlled by the command. The command is 13A24. This is the digital output command. So when you apply this command here, then you get the temperature, maybe the temperature from the 0 to 150 degree. Then your 0 to 150 degree where the analog input card, then you will see if the curve react like this, exponential style, this style. Then we could use the first order transfer function to represent your process system. We will use the curve function, apply a control signal, and then we can record the behavior of your process response. Okay? And once your process response react as this exponential style, then we could see we can use the first order transfer function to represent this process. Or in another word, if this exponential style curve basically can approximate your process reaction, we could use the first order transfer function to represent your process system. Once we decide the first order transfer function can be used for your system, then next things we need to determine the parameter of the first order system, the exponential frequency. As the first order transfer function, GS, maybe we can add a K again here. So as the first order transfer function here, how can we get this parameter here? Okay, and how can we get the gain? We need to recall some knowledge from the control theory. From the control theory, this GS, this is the first order transfer function. And if we apply a step response, a unit step response signal to this first order transfer function system, then the react transfer function will be this, CS. So a unit step signal, this is step input signal, okay? And then the react response signal, it is this. And once we transfer this S domain to time domain, so this is the react, this output react equation. So this time domain is easy for us to understand because the time domain, if we are using the HMI to view this time domain reaction, that's very easy. We can use HMI trend or PLC curve record function. We can record the time and the value. We can record the process response. For example, the x-axis is the time, the y-axis, this is the value of your process output, either temperature, speed, or pressure. Using the curve function, we can view the output, the behavior. Then how can we leverage this curve to calculate, to find the parameter of the first order system? The parameter A here is named exponential frequency, okay? And then let's do a little bit of analysis for this time domain. So when the t is equal to this 1 over 8, let's think about the equation. So the c, when the time get this 1 over 8 this time, okay, this is the time. Then this equation equal to what? 1 over e exponential here multiply this 1 over 8. Then this area will become minus 1, right? Then this equation will become to 1 minus, the power is minus 1. Then this value equal to what? This equal to 1 minus 0.37 is equal to 0.63. Okay, 0.63. That means if the gain of this transfer function is 1 and we applied 1 unit signal, then the response will equal to 0.63 when the time at this 1 over 8 this time. If we go back to this curve, we can see if this step response, if we give a 1 signal here, and the result is also the 1. If we can find the 0.63 result, basically that means if we can find from here to here, the 63%, if we can find the 60% of this value difference starting from the initial to the settling time here to the settling status here. If we can find the 63% of this result, then the related time here, this time we can get the 8. So if we can know the time from the curve, we can definitely find the time at here. This time the unit is a second. So once we can find this time, we can get this time. We can get the A parameter. This A named exponential frequency. Leveraging this curve, once we have this key and we can get the A, once we have this A parameter, then we can get this first order transfer function. Apparently, this is also a gain here. I can explain how can we calculate the gain of this transfer function. Okay, here I can use the DC motor. Take an example. For example, we can use the DC motor as an example. So if the DC motor, when the voltage is 0, okay, the voltage is 0 and the speed is 0 RPM, and then when I applied 2 voltage to the DC motor driver, then we can get the speed of the motor that become 400 RPM. Okay, and using this curve, that means when we applied 2 voltage, then we can see the motor will ramp up and become settling very fast. So while the motor becomes settling, then we can see the speed is a 400 RPM. Here is a 400 RPM. Okay. Then using this curve, we can find the 0.63%. We can find the 63% of this RPM where we are here. So let's firstly calculate 400 RPM multiply 0.63. Okay, this equal to 252 RPM. Then from this curve, when we record this curve, we can find when the value, the speed equal to 252, then we can find the time, which moment this motor get this 252 RPM. So for example, from the curve, we're starting from the 0. So after I this t, we got 0.5 second. Usually the DC motor can react very fast, right? So the t, when the t equal to 0.5 second, then we get this 252 RPM. Their initial status is 0. Then how can we calculate this A here? So the A equal to 1 over t. So 1 over 0.5. So that equal to 2. Okay? We can see we got this A. Then this GS transfer function will become 2s plus 2. This is our transfer function. Again, so as I mentioned, actually here it should have a gain. Then let me explain how can we calculate the gain. That gain means when we apply an input, the input has its unit voltage, right? The output has its own unit RPM. So what does it mean of this gain? That means the gain should equal to here. The gain is equal to the change of the output over the change of the input. So the change of the output is a 400 RPM. It's starting from the 0, right? And the input is 2 volt and starting from the 0. So that means this gain is equal to 200. Okay, then once we get this K here, we can see this transfer function actually is this. This is our motor, the DC motor, first order transfer function. By using this curve, this method, once we find this 63% of the difference change from this output, the speed, then we can find the time. Once we find the time, we can calculate the A parameter here. So this is the basic idea. How can we use the reaction curve to calculate the A parameter, and then we can get this transfer function. In this case, there's one simple assumption. So the initial status is 0. It's 0. So when we calculate this k, it's quite easy. We can get this 200. Because of the k calculate as this way, so the GS means what? The input, output, right? So the input and the output has this unit behind. So the output means RPM, and the input means watt. Because of the gain calculate by using the RPM here, and the input, this is watt. So this is the unit of this transfer function. Here, we need to be very carefully. So the very original style of the transfer function here, it doesn't have any unit behind. It only represents the behavior of the system. That's why it doesn't explain the k, the gain here. Once we apply the gain as a part of the first order transfer function, so this GS will represent something. Because of this gain here, this transfer function, we will have the unit of the input and output. Then this transfer function will really represent your real system. Okay, this is your real system transfer function. When you apply a voltage, then you can calculate the final RPM by using this practical transfer function here. Then let me use another example, the temperature. Okay, some cases, the temperature system can also react as a first order, this reaction behavior. So we can use another case, use the temperature as an example. Again, if you are using a PLC or any other regulator to control the voltage to a heater regulator. For example, if we regulate this voltage starting from the 1 watt to 5 watt, this is the input signal. And then the output of the temperature, while we apply the 1 watt, so the temperature was equal to 50 degrees. Then while we apply 5 watts to this system, the temperature become 250 centigrade. Okay? And during this change, we get this curve like this, exponential curve like this. Then let me demonstrate how can we calculate this GS, this transfer function. Okay, in this case, this is slightly different compared with the first one, DC motor case. The initial status doesn't starting from the 0. So the input start from the 1 watt and the temperature start from the 50 degree. Okay? Then when we calculate this 63%, we need to be very carefully. The 63%, this based on the temperature change. That means while the temperature become this settling here, the settling temperature is 250 degree, right? And the initial status, it wasn't the 0. The initial status is a 50 degree. So that means the temperature change, that was the 200 degree. Then when we calculate this is 63%, try to find the time constant, right? This spot equal to what? This spot is equal to 250 minus 50. Then we times 63%. And then we need to plus this base, this initial status. The initial status is a 50 degree. So the result is equal to 176 degree. Then from this curve, we will find the 176 degree and find out this curve and find when the moment the temperature got this 176 degree, how long we get there. So for example, in this case, the time we get there 90 seconds. Okay, 90 seconds. So take care, we have to use the second as a unit. Okay, so when we get this 90 seconds, if you recall here, the t is equal to 1 over 8, right? So a is equal to 1 over t, then 1 over 90. 1 over 90 equal to 0.11. Okay, this is the exponential frequency here. And once we get this a parameter, so we get this a here, the very important parameter of the first order we got there. Then we need to calculate the k, the gain of this transfer function. So again, this time the gain will equal to output, the difference of the output over the difference of the input. The output, the difference is 250 minus 50. So this time it is now starting from the 0. Okay, and the voltage also 5 watts minus 1 watt. Okay, this is the degree. Okay, this time the gain is equal to, denominator is 4, numerator is 200. Okay, it's a 50. So the 50, that means the input is a voltage and the output is a centidegree. Okay, this is the gain, the behind, what does it mean of that behind? So then eventually this GS, this transfer function, is equal to 50 multiply 0.11 S plus 0.11. So this is this temperature system transfer function. And here we need to be very carefully. So while we are using this transfer function, that input must be the voltage and output, this is centidegree. And other than this transfer function, we must write down this initial status, because this transfer function calculated from this initial status based on this initial status. So the initial status of the input is 1 watt and the output is 50. Okay, then when we are using this transfer function, so while we applied 4.5 voltage, the real input, when we applied as an input of this transfer function, the 4.5 voltage need to minus 1. So the real input of this transfer function must be, this is the real input of this transfer function. Okay, and the output, so when we are applying this 3.5 as a real input of this transfer function, then the output could get a result of 175 centidegree. Then the final output of the real system output, we need to plus. This output comes from the transfer function, but the real system output, the real system actual real system output should be 175 plus your base, your initial status. Then that result is equal to 225 centidegree. So this minus 1 minus this initial status, and consider the initial status of the output. This need to be very carefully while we are using the real case. Most of the cases, the initial status is not equal to 0. Alright, this is using the curve function to calculate this exponential frequency from this first order transfer function. And it's very practical. Basically, once you have the HMI curve or PLC signal curve function, you can apply the input to your system and record the output from your system. Then, using the similar way, using these two examples. One example is this DC motor. Its initial status is 0. And if your initial status is not equal to 0, then you can reference this second example to calculate your gain, your exponential frequency, and also write down the initial status. And once you get this first order system from this S domain, then we can transfer this S domain to Z domain. And once we get the Z equation, we can transfer the Z equation to the difference equation, and we can use the PLC to implement that. Alright, in this video, we mainly talk about those mathematical calculations. I know it will be a little bit boring. It doesn't include any practical operation, but the topics in this video is very important concept. Even you learned the control theory before, you will see in the book, most of the time they only talk about this equation. It doesn't include a k. But in the real world, we definitely need to add this k, and the k came from the difference change of the output over difference change of the input. Another important topic is the initial status. So most of the people, while they are using the transfer function to represent their system, if they ignore the k, ignore the gain calculation, or calculate this wrong, or ignore the initial status, or didn't record correctly of this initial status, then your transfer function cannot fully represent your process system. Then you cannot do anything of this rest of the calculation anymore. Okay, this need to be very carefully. And then to record this curve, I know in this video I didn't involve any operation things. You can review one of my video I recorded before. So if you go to my website, and then you go to the playlist, and then you go to the PID and the process object modeling. And then you go to the PID and the process object modeling, this playlist, and find out the PID2 modeling and the PID control. Learn the controlled process object. And once you go to this PID02, please review this video. And in this video, I explained to record this curve. There has some important items we need to be very carefully. For example, you need to identify the operating point. Basically, operating point can be seen as the initial status. So as we know, in the real practical system, most of system, they are not a linearized system. But we are going to use the linearized transfer function to represent the system. So the important concept behind that is when your system is operating based on your operating point. So near the operating point, we can approximate your process system as a linear system. That's why this is the basic concept behind. And also you need to identify the maximum and the minimum of your process value. Some system, it will be saturated after for a while if you turn on the heater for a long time. So the temperature cannot go on anymore because your system has a limitation, right? And in the meantime, you need to write down the delay time, dead zone, and the saturation, as well as the disturbance of your system. And then you can record your system response based on your bomb test. You can give the analog output to regulate your system, and then you can review the response of your system. Like in this video, from here to here, I apply a bomb test. Then you can see your system. This is my system initial status. So as we can see, it's an initial status that was 43.5 Celsius centigrade. And then the system going up, and here to here, roughly the temperature was around 50 Celsius centigrade. So this is my system behavior. As we can see, this shows exponential behavior. Then we could use the first order transfer function to represent this system. But in the meantime, you must be very carefully about this initial status. Alright, other than this video, I would also recommend you review this PID02. I will paste a link under this video. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.